is a lot simpler in style than what you've been hearing about. My thesis advisor was Watercraft. I was a student at the Observatory, and he used to joke with other astronomers that he had a student that had an extraordinary grasp of the obvious. So what I'm going to talk about here is real obvious as he's talking about me. So I'm going to talk about the observer's universe because I haven't been an observer my whole life. I want to give you a narrative about being an observer, but also being part of the discovery of the accelerated expansion of the universe, but from my own particular point of view, which is the one that I lived through. What I'd like to start out with is this very interesting quote from a book by Lemaitre on Lemaitre, from the atom of the universe. It says, an important philosophical assumption of Lemaitre, which is manifest from the outset of the Physique d'Einstein, is that the universe must remain accessible to human knowledge and proportionate to it. I'll come back to that first and then this talk, but think about what that means. So where do you start a talk as an observer? Process. Well, I like to start in this particular slide, a slide that most people have never seen before. This is a copy of one of the plates that Vesto Slipher took in 1912. If you look at the very top, it says September 17th, Andromeda Nebula. This is one of his plates where he measured the velocity of the Andromeda Nebula. You can see there are three spectra in the middle there. The upper and the lower ones, that's the iron arc. In the middle of it is the spectrum of Andromeda. If you look really carefully, if I can figure this out like this, you may be able to see the H and K break over here. So what's amazing about this is that the velocity that came out was extraordinary. It was 300 kilometers a second actually coming towards us. Now, stars have been measured, their velocities have been measured for many years, and there were some velocities that were rather large, but there was nothing like this. This was a revelation to astronomy at that time, that there was something that was moving this fast. As a matter of fact, if you go and you read Einstein's the paper on general relativity, he comments on the small motions of the stars as part of the justification for the observational justification of what he was talking about in the paper. He was not talking about velocities this large. This opened up the universe to, how can I say, to strange things that were happening. So one of the papers that Slipher published back then, which many of you probably have seen, is this paper where he talks about the velocities of the spiral nebulae. And as you can see, almost all of the velocities are positive. There are only a few that are negative. And so the few cosmologists that were working in the early 1920s, they all knew this. They all knew that most of the nebulae were moving away from us, which was also a strange result. Here are these huge velocities, much, much larger than stars, and most of them are moving away from us. The editor didn't catch it, so I don't know. So most of you have also probably seen the plate that's on the right. So that's the famous VAR plate that Hubble discovered the Cepheid in M31. That refers to plate H335H. That's the Hooker 100-inch telescope, the 335th plate that was taken on it, and the final H stands for Edwin Hubble. That was taken on October 6, 1923. Now, Hubble took a bunch of plates at the end of 1983, ostensibly trying to find novae, which were the subject du jour at that time. And he marked some novae with his pen here, and you can see he marked an N here also. I don't think he actually was the one that blinked these plates. I think someone else did. But it doesn't matter. The things that he was looking for were novae. And of course, you know the story. He also discovered Cepheids. Now, most of you, and probably none of you, have ever seen this before. So on the right is a plate that I have on loan from the Carnegie Institution. I was a Carnegie Fellow for quite a number of years, and they sent me this plate for other reasons. And I'd like to point out that, so here are the novae. You can see how bright they are. The star that Hubble discovered, the Cepheid number 1 that he discovered, which set the scale of the universe, is that faint star right there. Can you see that? He was that good an observer that he was looking over this plate for very, very faint objects, and he noticed an object that was appearing and disappearing right at the plate limit. He was an outstanding observer. I just marvel over the fact that his eye caught this as he blinked the plates back and forth. This object appeared and disappeared, because as an observer, when you take plates like this, the seeing changes, and so the objects at the very plate limit appear and disappear all the time. Seeing something regularly appear and disappear on a plate such as this, to me, is a remarkable achievement.
So I'm going to skip over Lemaitre for a little while, and I'm going to jump to the next sort of milepost in observational astronomy that at least was important to me. Zwicky is shown here on the left. I hate the photograph where he's going like this. It makes him, I didn't know Zwicky at all, but he looks like a clown going like this. He was, of course, a really serious, brilliant astronomer. Here he's standing in front of the 48-inch telescope at Mount Wilson, at the Palomar Observatory. But he wrote this book, which is a classic in observational astronomy. We don't teach much out of it anymore, but it really is a very interesting book. It's actually used probably more in philosophy classes than in astronomy. Because what morphological astronomy, it's a very dense book to read, but if you distill what it's talking about is that if you have no idea what it is you're looking at, you don't understand it, the way you begin to do science is you create morphological boxes, and you classify something, you put something in one box, in another box, in another box, and after you've classified a whole bunch of objects, you count up the number of objects in each box, and you publish an APJ letter. And then over time, you hope that those boxes begin to end up having physical significance. But the idea is you always start out with morphological boxes. But the thing about morphological boxes is if they don't disappear over time, chances are the astronomers that are working in the field don't quite understand what it is they're looking at still, which is very true of Type 1a supernovae, where we have 10 different subclasses at least of Type 1a supernovae. It gets to be absurd in astronomy. They're variable stars. There's a variable star class called RV Tauri stars. And for a while, the IAU was arguing over whether the star RV Tauri was a member of the RV Tauri class of variable stars. It now is, but for a while it was kicked out of the morphological classification. Okay, let's jump to the next astronomer. This is a remarkable paper by Alan Sandage, a remarkable observer. Maybe some of us consider him perhaps one of the greatest observers of the 20th century. He wrote a paper on the ability of the 200-inch telescope to discriminate between selected world models. And in this paper, he started talking about measuring these two numbers, H0 and Q0, here Q0 being the deceleration parameter. What's amazing about this paper is that in this paper, he tells you exactly how he's going to measure Q0. Now, many astronomers are not going to publish papers on their best ideas saying, I'm going to work on this subject, and oh, by the way, this is exactly how I'm going to do it. But Sandage was able to do this for one particular reason. He had access to the 200-inch telescope, and you didn't. So it didn't make any difference that he was giving up all of his ideas because he didn't have any competition at that point. Well, after Lick Observatory, I went to Mount Wilson and the Los Campanas observatories, ostensibly to work with Alan Sandage, and that's a whole other story in itself, how you can work with Alan Sandage. But when I was working with him, I was there because I was working on RLIRE stars, not in cosmology. He told me that there are only two important numbers to measure, H0 and Q0, but at the same time there's lots of interesting astronomy to do along the way. So he kind of drummed into my mind that really what I should be doing as an observational astronomer is, yes, study RLIREs, but in the context of doing cosmology. Well, Sandage and collaborators had this interesting idea of how to use Type 1a supernovae, which we now know is the explosion of carbon, oxygen, and white dwarfs, to measure distances into the universe. And we now know a lot about them. They're still extremely difficult objects to study because they have no hydrogen in them, and therefore the opacity of the material is very low per unit gram. And so these things are horribly in a non-local thermodynamic equilibrium. But if you think very, very generally of what a Type 1a supernova is, you have a star which somehow, a white dwarf which is approaching the Chandrasekhar mass, somehow it decides to explode, and it goes through to almost statistical equilibrium and produces two elements, nickel-56 and cobalt-56. Now, if nickel-56 and cobalt-56 energy was deposited completely in the supernova, you would end up with this red curve over here, because this is the exponential decay of nickel-56, and this is cobalt-56. But because the gamma rays leak out, the actual light curve of the supernova looks like this thing. And the maximum is given by something called Arnett's law, which relates the maximum of Type 1a supernovae to the amount of nickel-56 that is produced. So this is all becoming evident at the time that these three astronomers, Alan Gustav and Gustav's student Bruno Liebengut, began the Las Campanas supernova survey. Now for me, although there was a previous Hubble diagram by Charlie Cowell at Palomar back in the 60s, this really was the beginning, the pioneers of supernova cosmology, because Sandage and Tamon, with the help of Bruno Liebengut, who did this for his thesis, tried to find supernovae using photographic plates and then tried to do photometry of the supernovae afterwards. They completely failed. And it wasn't their fault that they failed. It was because the plates at that time that you would buy from Kodak had lots of plate flaws on them. And if you're trying to find supernovae by blinking plates back and forth, if you have plate flaws, it drives you crazy. And so they ended up not being able to find many supernovae because of the large number of plate flaws. Well, in 1986, I moved to Cerro Tololo, and having been sort of a student of Sandage, so to speak, Sandage urged me to pick up this project, but to also do it using CCDs. And so we had the first CCD in the Southern Hemisphere at Cerro Tololo on the 4-meter telescope. And in 1987, Mark Phillips and I published this paper, which is not referenced very much, but it actually, I think, is a very interesting paper, because in this we compared two supernovae, which were 86G and whatever the other one is. And we noticed that the light curves were different. Not only were they different, they appeared to rise and fall at different speeds, and the one that seemed to fall more quickly turns out to be the fainter one. And that's all in the paper, but this is 1987. This is well before the discovery was made. However, there was already a paper in the literature by a Russian astronomer, Psovsky, who also saw this in some much poorer data, but much larger amount of data from photographic plates. So although we found this in our data, it had already been pre-discovered by someone else. We started the CTO Bright Supernova Survey in 1986, and we produced all sorts of light curves, collaborated with Mark Phillips, Mario Jamoy, and you'll see Jose Mas in the next slide. Mark Phillips in 1993 took my photometry and came up with these relationships which relate the brightness of the supernova, where supernovae are bright over here and faint over here, versus how fast the supernovae evolve away from maximum light. So this is called the Phillips relationship, or as Mark Phillips likes to call it, the Psovsky-Phillips relationship. We then step into trying to do the work that Sandage and Tamon and Liebengut were trying to do. And we did this with the help of Jose Mas, who was a professor at the University of Chile, where we took photographic plates, we discovered supernovae, and then we followed them up with CCDs. And this is the calibration that we came up with. But what was amazing was this is the Hubble diagram that we came up with. And so here is redshift over here, and here is luminosity over here. This relationship here was so much tighter than any other Hubble diagram that had ever been made. For us, it was revolutionary. Over here, when we corrected to a dispersion of a little bit more than 1/10 of a magnitude, which is about 0.05, or about 5% in distance. That is, we could measure distances to objects way across the universe to 5% using this technique. Well, Mario Jamoy went up to Harvard and showed this particular diagram in 1993. I had been collaborating with Brian Schmidt, giving Brian some of our data on core collapse supernovae. Brian saw that diagram and got all excited. Now, the Klon-Tololo survey was created for us to calibrate Type 1a supernovae to measure H0 and Q0. That was what we set out with in 1989. And so by 1993, we had begun to work on trying to measure Q0. I had built a CCD camera and put it at the prime focus of the Schmidt camera at Cerro Tololo. In 1994, Brian over here, Pete Chalice, and myself started talking about how we could also do this on the 4-meter telescope. Now, we knew Saul Perlmutter's group was doing this, but we also knew that we had the calibration on how to measure distances, and Saul didn't. So we figured that we could catch up if we worked really hard. And so we put together a group, and I actually was the one that put together the rules of the group, and we had 2 rules in our group. The first one was that we would all as a group would work for 6 months and give all of the analysis and the data to a particular group at a university. And so we had different universities, our observatories, Cerro Tololo, ESO, Australian National University, University of Washington, Harvard, Berkeley, etc. And 6 months by 6 months, we marched down this list, piling on more and more data. And the other one was that whoever was the intellectual leader of the paper would be first author. And I'm really proud of the fact that the High Z Supernova team, which were one of the two teams that won the Nobel Prize. All of the papers we published except one, the first author was either a postdoc or a graduate student. It was not any of us senior astronomers. Okay, so we've now seen this. It's very nice to have both 3 Nobel laureates, Bob Kirshner and Alex Filipenko, to always give the talks on dark energy, because they have to explain all that stuff, and I get to talk on the stuff that I really like to talk about. So I'm not going to go over what Alex talked about, but what I do want to show here is that these are the 2 discovery papers, redshift versus distance modulus. Notice that the high Z supernovae clustered up over here, there are about as many of them as at the low Z supernovae. And this has now become a problem because the low Z supernovae now have the larger errors than all the high Z supernovae. And so you've already seen this diagram from Bertulli et al. And it's a very, very beautiful Hubble diagram. Notice that the low Z supernovae over here do not have remarkably smaller errors than the ones high redshift, which really says that at low redshift and high redshift our errors are being caused by something else. And as a matter of fact, we now have fewer low redshift supernovae than we have higher redshift supernovae. So the whole anchor of this whole process is now being driven by the statistics over here and not driven by the statistics over here. It's the low redshift sample that is limiting our cosmology at this point with Type la Supernova. Okay, the reality of photometry. I hate doing photometry. I've been doing it 40 years and I still can't stand it. You have to worry if the sky is cloudy. You have to worry about all sorts of things. Whereas the spectroscopist, all you have to do is start the exposure and wait an hour and then start another exposure. Photometry, you're always worried. But it's very important in order to do the cosmology. So here are some rough estimates for how good you have to be at doing photometry. So if you want to measure the range in the Hubble constant relative to the Hubble constant in terms of magnitudes, well, converting from distance to magnitudes is just the 1 over d squared factor. So if you want a 10%, if you have a 10% range in the Hubble constant, that is 73 versus 67, you plug that into this formula and you find that the range that you're dealing with is 2/10 of a magnitude. That's easy to do photometry, 2/10 of a magnitude. However, the equation of state parameter, which is what everyone wants to know right now, is much more difficult. The error in W over W is 0.4 times this. So theorists are asking us to go to 1% errors here. And if we have 1% errors here, that means that I have to do photometry to 0.4 millimagnitudes. The original LSST goal was 20 millimagnitudes. Now this number has gone down because we have to do precision redshifts. But no one is doing this level of photometry right now. It's impossible for us to do this. So we have a goal of really trying to improve the value of the equation of state parameter, but it is much, much harder than it is to do the Hubble constant, just from the simple facts of doing photometry. Most photometrists at best get down to 1%. There are a lot of other problems with doing supernova cosmology. These, to me, are the three big ones. And I'm sorry it's a little bit complicated because these are all astronomer units. But the first one is reddening. So in astronomer units, this is the color excess, this is the total to selective extinction ratio. But let me just say that this number here ranges somewhere between 1.8 and 3. We really don't know what the value is. It may actually range between those two. And we really can't measure this value more than to a few hundredths of a magnitude. So just right here, the errors on the reddening are at a few hundredths of a magnitude, which already overwhelms our ability to measure the equation of state. Now we can reduce that by going to root n statistics, but still, we do not understand the reddening law. In particular, we don't understand what it is that's causing the reddening, what the size of the grains are. We have these crazy reddening laws which are very steep, which look like grains which we see nowhere else except around Type 1a supernovae and Type 2 supernovae. So we are trying to use an object, we're not quite sure what it is that's exploding, we're not quite sure what the dust is around it because we've never seen this dust before except in one line of sight towards our galactic center, and we're going to try to do precision cosmology with it. We're working on it, but it's a tough problem. The other thing that few people know is the fundamental calibration. In order for us to measure something in the sky, the brightness of a star, we have to measure it relative to another star. And you would think that by now we would know the relative brightness of a star to a few percent. That is, what's the flux of Sirius at 400 nanometers? What is it at 1 micron? We actually don't know that to better than 1%. And as a matter of fact, we probably don't even know it to 2%. So I can't do K corrections better than that right now until we actually launch a satellite that does fundamental calibrations of the stars in the sky. And Gaia will help us with that, but we really need a dedicated satellite. This right now is the largest limiting factor in our ability to do precision cosmology. We don't know the relative flux of any object in the sky except the sun, but the sun is too damn bright and it's also out in the daytime and we're observing at night. So this is a real problem for us. And finally, this is something that we have been working on really hard and we haven't been able to break this nut. But we have this crazy correction in doing supernova cosmology where we say, okay, this supernova looks a little bit redder than this other one. We don't know why it's redder. It could be for two reasons. One is that, well, maybe there's some dust and it's causing reddening. But it also could be a cooler supernova. So those are two very different parameters. One's dust and one's the temperature of the pseudo-photosphere. And yet we assume that both of those have the precisely same color relationship. We lob them together into a single parameter. So we're lobbing together the temperature of the supernova, which is relative to the supernova, and the dust properties, which may not even be associated with the supernova, could be interstellar reddening. And we're putting that into a single parameter because so far we can't separate out those two. Something is redder because it's either cooler or because there's dust. And since we don't know what's blowing up intrinsically, we have not been able to separate those two. That one's really a scary assumption that we're still making. Okay, but those things we all know about in supernova cosmology. The stuff that we argue about, I'm only going to fortunately show you one particular diagram because this is real ugly stuff, is this. So I don't really want you to understand it very well. I just want you to accept the fact that this is a real scatter plot, and yet we're trying to pull some numbers out of this plot. We have here, this is from Andy Howell, by the way. We have here galaxy host for the supernova. We basically have here the Hubble residual. Is the supernova too bright or too faint? And so we take the Hubble flow, we calculate delta magnitude, whether it's too bright or too faint, and plot it versus the galaxy mass. We're plotting galaxy mass versus a supernova luminosity. So do you see a correlation there? Well, it's really hard to say, but right now in doing supernova cosmology, we are assuming that there is a discontinuity roughly at this stellar mass in a galaxy such that we apply this value, which is about 0.04 magnitudes for the low mass galaxies where the supernova go off in them, and we apply this value for the high mass. And we have no idea what's causing this so-called mass step. But these are the sorts of things that we are putting into our data to pull out precision supernova cosmology. Well, as I said, one of the real problems is that we don't have enough Type 1a supernovae at low redshifts. We've been working in the last 10 years. We just finished our 10-year program for the Carnegie Supernova Project, where we're recalibrating Type 1a supernovae using extremely well-calibrated filters and photometric systems. And we're now getting down to about a 0.1 magnitude range out in the near infrared where reddening is not much of a problem. And because the temperatures of Type 1a supernovae are roughly 5,000 degrees, we're also in the Rayleigh-Jeans part of the blackbody curve. This is not a blackbody, of course, but on the blackbody curve, where small changes in temperature really don't affect the colors very much. So we can do supernova photometry using these filters. So let me leave with the following few slides. The first is there are going to be future techniques for measuring H0. Alex Filipenko didn't have time to talk about this, but this is a technique that his team is going to use, where instead of using Cepheids, they're going to be using Myra variables. And so similar to the Levitt diagram, here is a period versus magnitude. The blue points are Myras that are oxygen-rich, and the red points are carbon-rich. And we can separate out these things easily using photometry. What's amazing about this, and this was discovered by a graduate student at my university, and just defended his thesis last week, is that this relationship has a dispersion of 0.12 magnitudes. That's as good as the Cepheids. So Myras may be able to be used like Cepheids, but the good thing about Myras is they don't just appear in young galaxies. They also appear in both late type and early type galaxies. So now you can go out to ellipticals, and instead of using Cepheids, you can use Miras both in ellipticals and in spirals. This will greatly increase the number of calibrators for the local distance scale. So let me leave with some really stupid questions. This is the obvious part. First question I have is, what defines the Big Bang these days? I have no idea. Is it the end of inflation or is it the beginning of inflation? I've seen papers written about this in both directions, and it's not particularly important, but I think it's important that we decide once and for all what we decide is the beginning of the Big Bang. Okay? Second, going back to Lemaitre, what defines the universe? Do we admit to operationalism, a word that Eddington coined, which is a concept believed by Lemaitre, which states that physics actually never achieves reality? Now, there's a great word from Christian theology, anagogy, which means the spirit behind reality. There are 4 different levels of knowledge, and anagogy is the final form of knowledge. It's also the same as the Platonic theory of forms. It states that there is a universal truth beyond everything that we can see in reality. And the question is, are we getting to the point where we're creating cosmologies which really are anagogies, because they are beyond the reality of what we can measure, but they're important parts of our theory. They're essentially a truth that is required for us to do our theories in. The thing that Michael Turner pointed out many years ago was, why is omega lambda roughly equal to omega m? What's causing this coincidence? The second coincidence is even weirder. The more we measure W naught, the closer it's getting to -1, plus or minus epsilon. Epsilon is now about 8%, but some people claim 5%. But as epsilon goes to 0, and this stays closer to -1, the likelihood that WA, the time rate of change of W, is anything else but 0 gets to be very small, because if there really is an oscillation in W going like this, what's the chance that we happen to be living right at the epoch where it's crossing through at -1? It's really easy to measure W. It's really hard to measure this. And then finally, and I'll show one more slide after this, another thing that is, some ways we're confusing words. It's not necessarily important for us to figure this out, but I just want to put it out here. As an observer, when I talk about the universe, I talk about the observable universe. But that has changed in time. We now talk about a meta-universe, a universe that's outside of our abilities to measure things, which I hope it never catches on, but I'm going to call it the anagogical universe, the truth beyond beyond the physics that the reality that physics can measure. And then finally, there's another universe that we're talking about, which is the one which I think is prior to the Big Bang, which would be called inflation or something before that. And again, I hope this doesn't catch on, but the word you would use would be U-universe, where Ur is the Babylonian city, and it means primitive. So I think there are 3 universes: the one we observe, the one that is beyond reality as we see it, and the other one is the primitive universe. So this is my final slide. The first photograph I showed you, those photographs were sent to me by a collector who somehow got a hold of Olin Wilson's slides from 1958. And so he was up at Castel Gandolfo, and he was visiting with these 3 astronomers, Father Martin McCarthy, Father Daniel O'Connell, and Father Flor Bertium. I knew McCarthy. I didn't know the other 2. I certainly knew this guy a lot because he is kind of the father of measuring light pollution. He wrote the first papers on the problems of light pollution for observatories. He was very much a polyglot. He was a theorist. He was an observer. Amazing man. But what I want to leave you with is that for me as an American citizen right now, it's kind of embarrassing to say that I'm from the United States, considering the strange politics that's going on. And the more it goes on, the more there is a wedge being driven through science and religion. Religion is used more and more in politics in the United States. And what I'd like to say here is that I would like to thank the Vatican Observatory, the astronomers here in the Society of Jesus, for giving us a platform where we can talk about both science and, if we want to, religion and theology in an environment where we're all very comfortable with it. Because right now in my country, in the United States, it's extremely uncomfortable to talk about these things. but I really appreciate the chance that I have to come here and to be in this very humanistic environment for us to talk about these particular issues.